Hi, everybody, and thanks for joining me on doing some supplemental related rates problems because I know when everybody woke up this morning, they were like, I need more related rates problems, especially supplemental ones. So that's what we'll do. Um, okay, all joking aside, we're going to work through a few problems. We're going to try to talk through the logic a little bit to see if we can help make these connect because I know these are always a challenge. So just stick with it, keep working hard because these can be difficult. Okay, so first things first. I always suggest we look for the thing that they're asking for and write the equation of that thing. So they're asking us, we jump right to the end, they're saying, at what rate is the radius changing when the volume is 400 cubic feet? So if we imagine this is a spherical balloon, which doesn't really exist, but that's beside the point. Well, maybe, I don't know. A perfectly round spherical balloon. And we're saying they want to know what rate is the radius changing? So they're asking for drdt. That's the thing we're looking for. So we know whatever formula we're going to take the derivative of, it better have radius in it. Now, the other thing they tell us is that the volume, we know that the volume is 400 cubic feet. So therefore, I'm probably going to want to use a volume equation. So the volume of a sphere, volume is 4/3 pi r cubed. All right, good news. That has a radius in it, and it has a volume in it. So this is looking likely. Now, we cannot substitute in values until after we take the derivative. So if gas is escaping from the spherical balloon, or being pumped in, whatever it is, if it's changing, you have to keep the letter. You have to keep the variable until after you take the derivative. So the volume would be changing if gas is escaping. The radius would be changing because it would be getting smaller. So therefore, I can't plug anything in. Can't substitute anything in. So we're going to take the derivative. Now, the key thing to keep in mind is we're doing the derivative with respect to time, not with respect to v, not with respect to r. So the derivative of v with respect to t, would be dv dt. Now, constant multiplier says I'm going to leave the 4/3 pi alone. Right? Just constant multiplier. And now I'm going to do the derivative of r cubed. So we start by doing chain rule. We start by bringing 3 out to the front, subtracting 1. Right? And now we say, all right, we did the cubed. What have I not done the derivative of? R. What's the derivative of r? Well, dr dt. Fantastic. Now we sub stuff in. We say, what do I know? What do I know? What do I have? What am I solving for? And so we go back and we look. And we say, okay, what do we know? We know gas is escaping from a spherical balloon at a rate of 10 cubic feet per hour. So therefore, I know dv dt is equal to 10. Now, we need to think very carefully because dv stands for the change in the volume. So if it's escaping, then that means the volume of the balloon is getting smaller. So I need to make sure I get that negative in there, right? The change in volume, it's a negative volume. That's decreasing. Okay. And then do I know, let's see, do I know R? Well, the problem didn't give me R. Okay, so what could I do to figure out R, right? Because I know dv dt, right? We could sub that in, right, if we wanted to. That's negative 10. I don't know R, and then dr dt is our goal. That's the thing we're solving for. So if I can figure out R, I'm done. So what I'm going to do is we're say, well, they did give me this piece of information. Maybe I'm supposed to use it somehow. That the fact that this is a spherical balloon that has that is 400 cubic feet. Oh, okay. Well, if I use that, if I take that idea, I say I already know the volume equation, right? Volume is 4/3 pi r cubed. So therefore, the volume is 400. So I could use this to solve for r potentially. So I'm going to multiply by 3/4. But whatever I do to one side, I got to do the other. So the 3 and 3, the 4 and the 4, they all divide. Leave me with 300 is equal to pi r cubed. Maybe divide by the pi. So this is 300 divided by pi equals r cubed. So then last but not least, we're going to do the cubed root. Leaving us with r is equal to the cubed root of 300 divided by pi. Okay, so there we go. We got everything we need. I know dv dt. That is negative 10. The 4 pi thirds is a constant. Oh, and actually, though, we have a nice little division here, right? We got the 3 and the 3 that can divide, makes that a little cleaner. So now it's not even that hard. Now it's only 4 pi times my radius, which is the cubed root of 300 divided by pi. This whole thing is squared. Dr dt. And as far as the cubed root goes, we could always rewrite that as a 1/3 power, right? Because so if this is more comfortable for you, we just say, okay, so this is 4 pi times 300 over pi raised to the 1/3 squared, and now a power to a power and multiply, so 1/3 times 2. So really, this just simplifies out to be 2/3 dr dt. And notice this problem does not ask us to round, so therefore the assumption is answers are to be exact. So we're going to go ahead and it's going to be pretty ugly. I'm just going to divide by this whole thing. So this is going to end up resulting in, I need a tiny bit more space. So when you run out of space on your paper, here's what I highly recommend you do. You go ahead, highlight your work, and then you make it smaller. Okay, now we have more space. So go away, keyboard. There we go. All right, so we're going to go ahead and just divide by 4 pi times 300 over pi to the 2/3 dr dt, which is equal to negative. Oh, sorry, divide by. Whatever I do to one side, I do to the other, right? So same thing over here. 4 pi times 300 over pi raised to the 2/3. And I'm not dividing by dr dt. That's what I'm solving for. So now the 4 divides with the 4, the pi divides with pi, that divides with that, leaving me with dr dt is equal to negative 10 divided by 4 pi times 300 over pi raised to the 2/3. And whatever that is. Okay? But this would be wrong, right? In calculus, we expect whenever you have context, you have meaning, you should have units. So we're going to go back and say, okay, this is describing change in radius. So if I can figure out what my radius is measured in, it's going to have the same units. So therefore, when I go back and look, I say, well, my volume was in feet cubed. So therefore, my radius must have been in, not FRs, whatever that is, it must have been in feet. So therefore, this is going to be the change in the radius. So this is going to be feet per change in time, dt. So we go back into the problem and we say, there we go. It was measured in hours, the other rate that I had. So therefore, this would have that same unit. So this is going to have feet per hour. There we go. There's our answer. All right, on to the next one. So now, this one is a circular griddle, and I have found that sometimes my students in person do not know what a griddle is. It's a pan, okay? It's a kind of it's a special pan, but it's a pan. You can Google it. So a griddle is being heated, and so when you're heating, it's usually made out of metal. So when you heat metal, it tends to expand. Now you'll notice that's not a lot, okay? So don't go like watching your pan expecting to see some massive change. But the idea is it is expanding even just a little bit. So when it's being heated, they're telling us the diameter changes. So the diameter, change in diameter. So it's maybe I'll use a capital D to make sure. So it's dd dt. The change in the diameter over time is 0.01. Now pay attention, is it getting bigger or smaller? Well, it's getting bigger when we heat it. So therefore it's a positive number. Okay, now when the diameter is 30 centimeters, diameter is equal to 30 centimeters, at what rate is the area of the griddle changing? Area of the griddle. So, okay, it's not a very exciting picture, but we stop and think about it, like it's a circle. And I know the diameter is 30. So how do I get the area of a circle? Area is equal to pi r squared. All right, cool. So this is looking pretty okay. So the problem is asking us to find the rate that the area is changing. So dA dt, the change in the area, is the thing we're looking for. That's our goal. So we need to write an equation that has area in it. We did it. Okay, and here's our challenge. Our formula has radius. So I am not going to try to get fancy. I'm not going to try to get creative. I'm going to be careful. I'm just going to say, look, I know a diameter is equal to 2 radii. So I am now going to convert this into the thing that we're talking about in the problem. So I'm going to say a radius is equal to a diameter divided by 2. So therefore, area is equal to pi times diameter divided by 2 squared. And so now I get to keep things in the units that they were given to me, and my formula is now ready for working, right? Because the problem they told me is they gave me the change in the diameter. They didn't give me the change in the radius, and we would have to be very careful to make sure that if we wanted to claim that the change in the diameter is half for the radius, that's not always true. In this case, it is, but it's not always true. So I find it much safer convert to the variables that match what you're given, and then you never have issues. So let's just do a tiny bit of algebra before we get going. I'm just going to square d over 2. D divided by 2 squared is d over 2. D squared over 4. And then what we could do is just kind of rewrite our constants off to the side. So this is really like pi fourths times d squared. So when I take my derivative now, right, with respect to time, this would be dA dt is equal to constant multiplier of pi fourths. Now, the derivative of d squared, so the 2 would come out to the front, leave the d alone. Okay, we did the squared. What have we not done the derivative of? D. So the derivative of that would be dd dt. All right. Yes, this is looking good because we said, what is the thing they want us to find? dA dt. It's in our problem. Now we go through and we hope we have all the information. Do I know d? Yes, I know d is 30 centimeters. Do I know dd dt? Yes, I know it's 0.01. So therefore, we're done. dA dt is equal to pi over 4 times diameter of 10 times dd dt, which is 0.01. And hey, this is looking pretty nice. So just a tiny bit of calculator work. 10 times 0.01. So that divided by 4, that would result in dA dt is equal to pi over 40. And you're done, right? No, you're not done. Watch your units, right? So we go back, we say, okay, this is change in area. So we go back and we find what were the units, for our measurements here. They were all centimeters. Well, an area is not centimeters. Area is measured in centimeters squared. So the area, change in the area would be centimeters squared divided by time. What is our time for this problem? We go back and find the other rate. There we go. The rate they gave us was minutes. So therefore, this would be centimeters squared per minute. Now, of course, this is a very meaningless answer, right? Because the who knows pi divided by 40. So in the real world, we'd probably, convert it. We'd probably make it into a decimal and we'd say it's approximately 0.0785 square centimeters per minute, something like that. But if the problems don't say it around, don't round. You put your units, you keep it exact, and you're done. But to be able to visualize and kind of think about that, we're like, okay, it's 0.07 or 0.08 of a square centimeter. Very small. Okay. All right. On to problem number 3. All right. Now, these are our favorite. I'm telling you right now, we love ladder problems. When I say we, I mean teachers. Okay. So, all right. First thing, we like it because students can visualize ladders. There's very, very rare instances where I say, does everybody know what a ladder is? And somebody's like, I don't. So a ladder that is 20 feet long leans against a wall. Now, when we're drawing a picture, I always teach my students, or I say to my students, if it's changing, it gets a variable. If it's constant, it just gets a number. So this 20-foot ladder, if it's not changing, if they don't tell us it's a collapsible ladder or it's breaking in half or something of that nature, it's just 20. Okay, so we're going to keep reading along. As a ladder 20 feet leans against a vertical building, if the bottom of the ladder slides away from the building. Okay, so the bottom is sliding away. So maybe we'll call that distance x. The distance from the building, to the edge of the ladder, we'll call that x. Going from here to there, something like that. Now, they're telling us that it slides away from the building horizontally at a rate of 2 feet per second. Okay, so I know the change in x over time is equal to 2. Great. Now, is that a positive 2 or a negative 2? Well, that value of x, right, if that ladder were to slide out further, that x would get longer, so therefore it's a positive change. It's getting bigger. Okay, so now what? How fast is the ladder sliding down the side of the wall? So the question is this. So maybe this is height. They're asking for dh dt. This is our goal. So dh dt. But they are telling us when the top of the ladder is 12 feet above the ground. Okay, so therefore we do know that h is 12. Cool. All right, so now what? Well, that's kind of it, right? So we need some equation that has the height in it, because that's what they're asking for. And we don't have any information about area or volume or anything of that nature, so we'll probably try to avoid those. So we don't have any information about angles. Maybe we could try to use an angle, but I would say try not using angles first, because we know a whole bunch of information about the sides. So what I'm going to suggest is let's try Pythagorean. Let's do x squared plus h squared equals 20 squared. Why am I not subbing in my values for x and h? Well, because throughout the problem, they're changing, right? This ladder is sliding down the wall, sliding out, so therefore those numbers change. We can't sub in our values until after we take the derivative. So why am I able to sub in the 20? Well, because it's a constant. It's not changing. And if you think about it, you're like, okay, maybe if you did call it L, we would say, what is the change in the length of the ladder over time? What is dL dt? Well, that would be 0. So if I'm going to do, because it's not changing, so if I was going to do the derivative of this, it's fine to have the number in there, because the derivative of 20, or 20 squared, is 0. It works out just how we expect it to work out. So that's why I always say when it's not changing, it's okay to sub in the number, because the derivative takes care of any of the issues. Now, all right, so we have a squared plus b squared equals c squared, Pythagorean theorem, or x squared plus h squared equals 20 squared. Fantastic. Now, let's take our derivative. So the derivative of x squared, the 2 comes out to the front, we subtract 1, we say, okay, great, that's 2x. Then what have I not done the derivative of? X. dx dt. The rest of these follow the exact same logic. The derivative of h squared would be 2h. Okay, what have we not done the derivative of h? So therefore, that would be dh. That should be a capital H. dh dt. And then last but not least, what's the derivative of 20 squared? Well, 20 squared is 400, but it doesn't matter. There's no variable. So therefore, the derivative of it is 0. Well, okay. So now we hope and we pray. We say, what do we know? What do we have? What can we do? All right, so let's see here. 2, do I know what x is? Did they tell me the distance that the ladder is from the wall to the building to the ladder? And they don't. They don't tell us. Okay, we would have filled it in otherwise. So we'll leave that there for a second. Now, the one thing I do want you to say is, could we get it? Well, I know the height is 12 at this moment in time. I know the ladder itself is 20 feet. So I could do 12 squared plus x squared equals 20 squared. Okay, so let's just do that, and then we'll fill in our x. We won't do it in 2 steps. So 12 squared is 144, plus x squared is equal to 400. So now I got to subtract. I need to go 400 minus 144. So that's going to give me x squared is equal to 256. And of course, all of my math, computer science folk out there, they're like, I know that number. All right, so the square root of 256 is 16. So there, great. Okay, so the distance that this ladder is away from the wall is 16 feet. So I'm able to go ahead and fill in 16. So I know that the x is 16. Now, do I know dx dt? Yes, that is 2. Plus 2 times, do I know the height? Yes, that was 12. Do I know dh dt? No, that's what we're trying to find. And last but not least, do I know 0? Yes. Okay, now what? Well, no, math. Okay, so 2 times 2 times 16, so that's the same thing as 4 times 16, so that's just 64, plus 2 times 12 is 24, dh dt, which is equal to 0. And we're just solving for our dh dt now, so I'm going to subtract 64 from both sides. So that's going to go ahead and give me 24 dh dt is equal to negative 64. And then 64 divided by 24 is going to be dh dt is equal to, like I said, negative 64 divided by 24. We say what goes into them, and that's going to simplify down to be negative 8/3. So we're going to go ahead and put our units, right, before we forget. So easy to forget. So it's change in the height. The height is a linear measurement, so it's just going to be feet per, and then we go back in our problem and we say, that it was measured in seconds. The other rates were measured in seconds, so it's feet per second. Now, of course, we want you to stop and say, does my answer make sense? Does it make sense that the change in height is a negative value? We say, well, yeah, because it's sliding down. The height was 12. After it slides, it's going to be less than 12. It's getting smaller, so therefore it makes sense that it's a negative value. Always do that check. You can catch all sorts of goofy little mistakes just by doing a second of logic. All right, last problem. You've almost made it. Yes, we've almost made it. All right, so car A is traveling west at 50 miles per hour. Okay, so those of you who don't remember, north is up, south is down, and then it spells the word we. Okay, so, or never eat soggy waffles, however you want to look at it. I like the we, it gets me the right orientation. Okay, so what do we know? Car A is traveling west at 50 miles an hour. So I'm going to say like maybe here is car A, it's traveling west. So I know the change in A over time, the change in the distance of A, whatever, is equal to 50. Nope. Yep, 50. 50. Okay, car B is traveling north. Car B is traveling north at 60 miles per hour. So therefore I know dB dt is equal to 60. Both are headed toward a intersection of two roads. Okay, so we need to adjust our picture. Here we go. Let's try this again. There's an intersection. Car B is coming up this way, right? So therefore, dB dt is equal to 60. And A is heading west. Here comes A. So dA dt is equal to 50. And see, just a quick little change in just where I put the tips of my arrows describing the movement. We can now see they're heading towards each other. Okay, cool. At what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection? Okay, so let's go ahead and imagine this. All right, so here's our intersection, and here's A coming in that direction, and they're saying the distance from A to the intersection, so the distance of A is 0.03, okay, and then the distance of B to the intersection is 0.04, both miles, okay. So now, what are they asking? At what rate are the cars approaching each other? So kind of what is the distance from each other, right? How far apart are they? What is their distance? Hey, we just drew a triangle. We've never seen that shape before. Okay, so we want to know the change in the distance. So I need some equation that has distance in it, and that's going to have the something to do with the A's and the B's. Well, this seems pretty much like the last problem, doesn't it? It's d squared, a squared plus b squared equals, well, in this case, d squared. A squared plus b squared equals d squared. So therefore, what can we do with this here? We would say, again, the derivative. So this is 2d dd dt is equal to 2a dA dt plus 2b dB dt. And now we hope and we pray, we sub in everything we know, and we say, okay, do I know how far apart they are from each other? Do I know the distance? No, but I can get it because I know two of the sides of my triangle. I know a squared plus b squared is going to equal d squared, and I know a is 0.3. I know b is 0.4. And for anybody paying attention, therefore I know D is 0.5. So we'll solve for it though. It's a 3, 4, 5 triangle, D squared. So if we work this out, zero point 0.3 squared plus zero point 0.4 squared, that's going to equal 0.25 when I add them. So then when I take the square root of that, that's going to be 0.5 is equal to D, right, when I do the square root. So, okay, cool. So we know D. Do I know dt? No. But that's the thing they're asking for, the change in their distance. Great. Do I know A? Yes. Do I know dA/dt? So I'm looking right here. Do I know A? Yes. A is 0.3. Do I know dA/dt? Yes, that's 50. Do I know B? Yes, 0.4. Do I know dB/dt? Yes, that's 60. So we are rolling. This is going to be great. So we could just go ahead and start subbing things in. So this is going to be 2 times 0.5 times dd dt. It's just fun to say. Times 2 times a, which is 0.3, times dA dt. dA dt is 50. Plus 2 times b, which is 0.4, times dB dt, which is 60. And just to make sure we're crystal clear, all I'm doing, I would hate for you to be at home and saying, where's this coming from? All I'm doing is subbing it in to this equation. That's all that's happening here. It's nothing magical. So go away, keyboard. So I'm just, subbing in d is 0.5, dd dt, I don't know it. 2 times a times, right. Okay, all right, so now comes math. 2 times 0.5 is 1, so that's just going to leave us with dd dt is equal to 50 times 2 times 0.3. That's going to give me 30 plus 60 times 0.4 times 2. That's going to give me 48. So therefore, dd dt is equal to 78. And then, here comes the fun part. We have to put them together with our units, right? We have to say, what is the distance? Well, the distance in this was measured in miles, I do believe. Yes, miles. So therefore, this would be 78 miles per, and then our measurement of time. Well, our speeds were all in miles per hour, so this would be miles per hour. And does it make sense that they're coming together at a speed faster than either of them are traveling? Well, yes, because one of them's going 50, the other one's going 60. So they're both not one, they're not staying still or traveling right towards each other. They're coming at an angle. So it makes sense that it's faster than either one of them, but not the total amount of both of them combined. 110 if you do 60 plus 50, because that would be if they're coming straight at each other, then the distances would come together. All right, so therefore, whoops, didn't mean to erase that. I was trying to put a box around it. There we go. So there we go. All right, hope this makes sense, and keep at it. I know these can be challenging, but hopefully this helps clear some stuff up.